All right. Okay, so let's start today. So for today, I was thinking to continue on Stegatron on our image steganography tool. And last time we were, struggling with FFT. We were not really able to figure out why it wasn't working properly. I guess the FFT algorithm itself was fine, so I haven't made any changes into the signal.c file. And yeah, I mean, this part was kind of generated with ChatGPT, but it was like just trying to figure out why our implementation wasn't working. So, I just copy pasted this code into ChatGPT and asked it, why isn't it working? And it kind of came up with like this was the part that it did differently with mallocs. Not exactly sure why this helped. I mean, the DT implementations, it's still the same as it was on Wikipedia when we were looking at it. So we tried to implement this part in the pseudocode, and I mean, the results were kind of fine. And I think even with our old implementation, this new method would have worked probably. Not sure, I haven't tested it. But yeah, again, like the FFT hasn't really changed. It's kind of the same except these extra mallocs, which yeah, whatever. And yeah, so the implementation of FFT is the same as this pseudocode, but then in the stack.c file, I figured out some things from doing a bit more research. And what I found is that people usually use this, or I guess in this project at least, fdsig. I found that this guy or girl, I don't know, was using this centralized function, and this function will compute some low and high values. I'm not exactly sure what it does. I mean, I just translated it from Python into C. It was kind of magic, so I'll give it that. But yeah, it kind of gives you the low and high values from the like the image, and it also normalizes the image between 0 and 1. So that's kind of the point of this function. And what we were trying to do in the hide FFT function was that in our FFT channels, we were trying to put 0.5 if our payload was 1 and 0 if the payload was 0, right? We were trying to modify like the fraction part of the FFT signal to be like below 0.5 or above 0.5, depending on whether it's 0 or 1 and in our payload. And that, I think it was a value way too small for like the inverse FFT algorithm to keep it like the same. So it when we were doing the decoding of the secret, it was like all over the place, right? It didn't have like the right values. So that's why I thought maybe there is some other way of doing this, maybe adding a larger value, and that's exactly what I found. And this alpha is usually between 0 and 40 from what I debugged. Like here I was checking what this difference is, and it's usually 40. So yeah, it's way larger than 0.5, so that's maybe a factor. But now you might notice that, before we were just using the fraction part, and we knew that if a number is below 0.5, or I guess the fraction part is below 0.5 or above 0.5, we kind of knew how to deal with that. Even though it wasn't working, it was like a good concept. But here we add, basically, if you think about it, it's a random number, right? We just add a random number to our signal. So it's kind of like, okay, but how do you actually get the information back if you just add this kind of, random number? And the idea is that with FFT, from also what I researched, was that usually people use the original image as well as the modified image. So in the decoding part, you kind of need the original image, which initially I thought it kind of sucks, but it kind of makes sense, because if you're trying to communicate with someone and you're using FFT encoding, um, probably a strategy of setting up the communication is to first share a common image only you two have, and then that works as a decoding key, so no one else can find the signal unless they have the original image, right? And that's kind of what I remember I had to do for that CTF I was talking about. I think there was like an image from the internet. If you searched for like some keywords, it was the first image on Google, so it was pretty easy to find the original image. And even though maybe the image was compressed or it had some changes than what the original image that was used was, so maybe the original image was a bit different because of compression or stuff like that, but from what I understand, FFT is pretty good at dealing with those cases. So even though the original image is a bit different, you can still get decent approximation of what the message was, and you'll see that in the when I'll show you the example. But yeah, basically what we have to do is to just subtract from the encoded image, we have to subtract the original image. So that's how we get the difference, though it makes sense. And then we just multiply it with 255 and we get a color image. So that's kind of what I did, and it started to work. So pretty simple changes, I would say. And from last time, we have the Lena PNG image, which classic, and then we have this payload with a dog, really small image. I did like a 128 by 128 so that it fits inside of the Lena PNG image. And as you might be able to see, this image looks fine, like even though it has some artifacts in the corners, it's decent, like it's not that changed. So I would say FFT looks to work fine, I would say. Right, and then when we try to decode, so we do show FFT, and here we have to provide the original image, which as I said, it works kind of like a secret key, right? And then we have to provide the encoded image, and then we get the output, and the output looks kind of interesting. So it's first of all, it looks like it's mirrored, and that's mainly because first of all, I do manual mirroring. So here you can see that I mirror this on the columns. So if we remove this one, usually we want to mirror stuff just in case the signal gets really distorted and you need to try and do some error correction. But maybe we'll get into error correction as well at some point, because that could be interesting. It's kind of related to this topic, but it's not necessarily for this thing. So here we hide the image again, but this time we don't do any mirroring. And what I found interesting was that FFT itself still mirrors the image, right? But on the diagonal somehow, I'm not sure how. But as you can see, I think the quality is worse if you don't mirror the image manually as well. So I don't know, maybe it's just an impression, I guess, but I'm pretty sure it looks better when I mirror it twice, or I guess when I mirror it manually. Yeah, honestly no idea why. I guess it's because of that centralized function, which honestly, don't ask me, I have no idea how it works. It's just magic, in my opinion. But yeah, if you mirror the payload, it actually looks better. So that's another thing that I changed. I added this mirroring. So yeah, that's kind of all we had to do for FFT. So FFT actually works now. What I'm kind of disappointed, I mean, I didn't know about that, but when I wanted to add FFT, is that it kind of only works with image payloads. Like if you try to hide some bytes and then make sure that the bytes are the same when you decode the image, it's kind of not really possible. Like the payload is gonna be like the decoded message is gonna be way too different. I'm not sure why that's the case. Mm, but yeah, maybe maybe that's how FFT works. It's not really precise, so that was the problem. And to you know, I also tried to look into DCT, the cosine transform, and to be honest, I guess LSB has the highest capacity of hiding as much data as possible. Although I don't think it's really, when you do steganography, it's not really about how much data you can hide, but how well you can hide it. Because obviously LSB is the easiest to figure out. It's like the easiest decoding algorithm you can implement. And if you don't have any like encoding of your message, like maybe using RSA or like a SHA key, or I don't know, maybe even XOR, right? It's really easy to figure it out. For FFT, it's a bit more complicated because you need the original image, which already adds like an encryption key to it. So yeah, and maybe DCT is, we'll see today, because we are gonna try to implement DCT like from scratch in a separate main.c file just to see how it works, and then we'll take a look at how how it actually we can actually use it. So let's yeah, let's try to start working actually on DCT. And first, let's maybe take a look at the algorithm itself from Wikipedia, how it's supposed to work, like how do we want to implement the DCT function. There are quite a few, like DCT-I, DCT2, 3. Honestly, I'm not sure what all of these are about, but what I saw is that DCT2 is, let me zoom in a bit. This is what it's usually referred to as DCT. So probably this is the formula that we want to implement, right? And reading around here also saw that about this information, that you want to add some alpha to this formula, right? And we are gonna try to do that, because what I noticed is that if you don't use this like normalization term or whatever, the value gets quite large and it doesn't look right. Okay, so we are gonna try to also use these things, and I don't know about that, but what I noticed was that there is no inverse like formula. And what I kind of figured out was that to get the inverse, you still use the same thing, but you just swap lowercase x with capitalized X, and it kind of works. It's kind of strange, but that's what I figured out. So it's kind of interesting. No idea how the guy came up with this thing, but it works. Like, sure. And I guess how it works, it's kind of, I mean, I have no idea, honestly, but you can see the pi, so it's kind of like an angle in here, and then uh, n over capital N, it's kind of a number between 0 and 1, and then you have k, which is like, you can think of it as a number of rotations maybe, and you also have a 1 over 2, which is maybe like a phase. So in here you kind of have an angle inside of the cos function, so it's always anyways going to be a number between 0 and 1. So it kind of makes sense to divide it by something, because it's going to be 1 plus 1 plus 1, right? And we kind of want a number between 0 and 1, so it kind of makes sense to normalize it somehow. But yeah, like the actual meaning of what the cosine term means, honestly, no clue. But you know, as engineers, if it works, it works. We don't ask questions. I mean, I'm just kidding. Obviously, it would be interesting to kind of figure out why this thing works, but you know, not really important right now. But yeah, anyways, like this is the formula, much simpler than FFT, I would say. But as you can see, it only works for 1D, like one-dimensional things, right? We only have one index, but we want to use it for an image. Okay, and obviously, spoiler alert, if you scroll a bit down, you actually find the 2D version. And the 2D version is just the 1D version, but twice, right? So instead of using only one cosine, it uses two of them. So it kind of uses one for each index, which makes me think that for three indices is going to be the same, but with three cosine terms. So again, like multidimensional, you just add another cosine term, which is kind of easy to do, I would say, like pretty easy to generalize this formula. But yeah, let's try to actually implement this thing. And let's go ahead and create a new main file. Let's start with, I'm gonna implement it in a separate project because I think it's easier to visualize like only the changes that we have to do. So let's start with hello world. Okay. 0, and then we just, I mean, yeah, history command, always compiling main.c files. So yeah, all of this works. So let's see now how we can actually implement this DCT stuff. So let's create like maybe a static void. Oh, and another thing that's kind of interesting about DCT is that you are kind of supposed to use it on blocks of 8 by 8. So we are gonna try to do that. And we'll see about the encoding algorithm, how we can maybe improve it, because this one is by far the one that can fit the least amount of data, because you can fit only one bit in an 8 by 8 block of pixels, so that's really small. But yeah, anyway, so let's do like DCT on an 8 by 8, right? So this thing is gonna get as an input I think it's gonna be a const double lowercase x, an 8 by 8, and the output is gonna be capitalized x and an 8 by 8. Right. So yeah, we're just trying to implement this formula. Okay, so let's use the indices the same as they are shown here, like k1, k2, n1, n2. We already know. Maybe we could define like block size as 8. block size. Okay, so we kind of need to iterate over k1 and k2 first because we want to compute x of k1 and k2. So let's do that. K1 is less than block size k1 plus plus, and then we need the same thing but for k2. Okay, then since this thing is a sum, we need a sum variable. Obviously, so double sum is equal to 0. Then we're gonna have some other for loops, so let's do I got to do other for loops, and then we need to set x at k1 k2 is equal to sum, right? And as I said, or I guess as Wikipedia says, you kind of want this alpha term, right? This normalization factor. So let's have like a static double alpha, and this thing is gonna get as an argument k, and it's gonna return a double. So here it says that if k is equal to 0, then we want to return 1 over square root of n. So we are gonna do like sqrt 1 over block size, and otherwise it's sqrt of 2 over block size. Right, so that's kind of the formula. Let's do okay 1.0, and I think we need to include math if we use sqrt. Okay, so here if we take a look, here it says we want to multiply our sum with alpha, so we could do alpha of k1 times alpha of k2, and since it's 2D, we have to do the same thing for each k index. That's kind of the idea, which pretty nice that it generalizes this easily, in my opinion. So let's try to get this sum working. So the sum is over n1 and n2, so let's just continue using those variables. Usually like to, if I copy like a formula from Wikipedia, I like to use the same variable names, at least until I make sure it works. Afterwards, you can change them, but yeah, like just making sure that everything works fine. But to be honest, I don't see any better names for these things. It's like, sure, it's the k indices. Like k index is gonna be for the DCT transform, and n index is gonna be for indexing into the image block. Let's call this one actually DCT block, or maybe you need an extra underscore. Okay, block x by 8 by 8, 8 by 8. What the fuck? Okay, so let's do this for loops, right? We did them. So here we need to compute the sum. So the sum is just adding this cosine term. So let's do sum plus, and then let's try to write the cosine terms. So we have pi over n, that's n pi divided by block size, and then we multiply with this parentheses, so multiplied with n1 plus 0.5, and then we multiply with k1. And honestly, that's it, like pretty straightforward. So let's do the other one as well. This one is n2 and multiply with k2. So that's just all this DCT has to do, basically. Okay, we are coding a image steganography tool, and right now we are implementing the DCT version, and in the previous two parts we did LSB encoding and FFT encoding. So this would be like the final algorithm we are trying, and then maybe we are gonna take a look into algorithms used for like applying some secrets on the payload so that they are, not in plain text, and maybe some error correction algorithms like Hammond or something like that. We'll see if those are good ideas. I mean, we are going to implement those only for the LSB implementation, because I have a feeling that for FFT you don't really need it, and for DCT I'm not sure yet, but LSB, it's kind of weak. It's like a pretty dummy implementation, but it still works. So yeah, we have this DCT function that takes in an 8 by 8 block and it applies DCT on top of it. So we should get back some, discrete Fourier transform or cosine transform, sorry. And in this thing we can hide stuff, and once we transform it back, it should look the same. So that's kind of the idea. So let's try to implement the inverse now, and see if it actually gonna work. So let's call it inverse. So this one is gonna take as an argument capital X and is gonna return lowercase x, right? So it's gonna be pretty much the same code. We just need to swap the indices around. So at this point we are computing lowercase x, and as I said, for lowercase x we want to use n as the index. This alpha cannot be here because alpha uses k, and we also need to swap these for loops around. So yeah, I guess I need to do one more. Okay, so we are going to iterate the n index because we want to compute lowercase x. Then we iterate the k indices because we want to index into, well, here I guess I forgot about something. I forgot about the important term, which is xn. Pretty funny, but let's do plus equals x at n1 n2, right? We forgot about that, but doesn't matter. So plus equals capital k1 k2. And what's interesting is that I saw that if you keep these two cosine terms the same, it works. Again, kind of no idea why it works, but it actually works. And the other thing is we need to add the alpha terms here when we multiply with k1 k2. So yeah, that's also something we need to add. So here you add the alpha terms when you set capital X, and here you need to use the alpha terms when you get the capital X term. But the rest should be kind of the same. So as you saw, we just had to swap these for loops around. The cosine terms stay the same, and you just need to swap capital X with lowercase x. So yeah, hopefully it kind of makes sense, at least from the implementation perspective. Like, again, I'm not a math expert, so I have no idea what DCT is actually doing behind the scenes. So I just see it as a formula, it works, so we just use it. So yeah. Okay, so let's actually try now to apply DCT on something. Let's actually use Copilot to generate some dummy data. So we are gonna have something like double dummy data, and let's make it block size by block size. And let's maybe use Copilot for this thing because it's, you know, just to get some dummy data. Right. Okay, I mean, I'd like some bigger numbers because would be more interesting, like 69.0, oh, 32.0. Let's wait. Okay, so it gives us some larger numbers. Is it 8 rows? Yeah, perfect. So that would be the dummy data that we are going to use. So we are going to pass it through the DCT block, then through the IDCT block, and let's see if it's going to be the same. So we are going to do DCT block. Let's pass dummy data, and then like capital X. We need to define capital X. Maybe equal to 0. And then let's do inverse. And we want to X and dummy data. And then maybe let's print. So size T. Let me just copy paste. Okay, perfect. So now let's try to print F the data. So print F for double numbers. I think it's still F. I'm not sure. Usually I don't use double data, which is kind of an interesting thing. And then let's print F a new line. Okay. I don't have a make, but let's see. Okay. Actually, it looks a bit trash. Like, I mean, we used alpha properly, so I don't think that's an issue. Hmm. It's kind of interesting. Not really sure. So I did DCT on the X thing, then back. Maybe we have to reset dummy data to 0 or something. No, we are just setting it here. I mean, this part looks fine. Let me double check with what I implemented in here, just to not waste that much time. So for the DCT block, I mean, we can just copy paste this, right? See if what's different, because it's basically the same thing I was trying to do yesterday. So this would be the DCT block, so it should be the same, and I think it is. Right, we iterate over the case, we compute the sum, we multiply with the alpha term, so it's the same thing. Did I do something wrong with the alpha term? No. I can also copy paste this one just to be sure, but the alpha term, I think it's fine. Yeah, there's nothing wrong with it. And what about the inverse? Maybe I did something wrong there. Now iterate over the n terms, over the k terms. Okay, it's kind of weird. Wait, what the fuck? I have an idea. Let me just, we are gonna copy paste this file into like main2.c. I'm curious what the diff is, and let's undo until we get to this point. And let's diff. Wait, what the fuck that do different? Okay. Just to make sure that I wait. Oh my! I did plus for some reason. I don't know why. Don't ask me. I did plus. Okay. I mean, here it was multiplication, just if anyone was confused. Okay, it was, I don't know why I did plus. Yeah. Okay, so that was, I think that was the issue. For some reason I was doing plus. Okay. So you can see that if you apply just DCT block and then inverse DCT, you actually get the same values as you had. So that's kind of nice. Like we show that this thing works. So now maybe you might ask, okay, but how can you use this 8 by 8 on like an 1500, like 500 by 500 image, right? Okay, I mean that's an interesting thing. We can try to load an image. So let's just stbi load. Let's load an image. We're just gonna copy paste something from here. So let's replace this stuff, why not, with loading an image. We're gonna need a few things though, but that's fine, like image read, image write. Do I have something like stb image? I guess I can just copy paste stb image and stb image write. So we should have these two things. We just need the implementation for them. Let's put that here. And we are not gonna use, we're just gonna exit. Okay, so the image path, it's just gonna be another png. We're gonna hard code some things. For uint8, do we need stdint? I think that's what we need, but maybe stddef is also an option. Okay, it wasn't. Okay, I mean, I'm pretty sure it's stdint, so let's just do stdint. Okay, so we load the Lena image, and as I said, this one has a different width and height, so we need to do something about that. So let's start with a for loop. So let's do for size t, and let's say I is the index of the block. I and j are gonna be block indices. Yeah, I'm curious what this. Yeah, like we kind of have embed text and extract text. These you can embed, I mean, you can embed text with DCT, but for text right now we are using the LSB implementation because that's the only one that allows us to actually write some text and get it back. But after today we'll be able to also use DCT for that, so that's So let's do width, and we have to divide by block size because we want to iterate the blocks. Okay, and we need to do the same, but with j for the height. Let's use j for the height and I for the width. So I is gonna be columns and j is gonna be rows. Okay, so now we need to maybe define capital X is equal to 0. Okay, so this is gonna be our dct transform. Let's have a helper function maybe for extracting a block, or maybe for applying dct on an offset. Let's think about it. So I mean, I just want a function that gives me the block. Sure, we could do that. So let's do a static void image to block. It's gonna take as an input uint 80 bytes. It needs the stride, so the stride is gonna be width times the number of channels, so it's the same like when we save an image with stb image. And I think we need a reference to, I think we might need a reference to the block where we are gonna write. So double x block size, and maybe that's it, I guess. So let's do 4. Actually, I'm gonna do a for loop like this, and we can say something like x, but n1 n2 is gonna be bytes, and here we need to compute an index. So the index is gonna be, let's think about it. So we want to copy, so stride is gonna be what we have to multiply, and we also need the I and j values. Size the I, size the j. We need the block I and block j. Okay, so obviously we are gonna do something like maybe I, as I said, I is gonna be, it's iterating the width, so maybe we actually have to use j there. All right, so this is the block column, this is the block row, and if we multiply the block row with stride, we should get like j times stride plus I. This is the index of the first element, right? And then if you think about it, let's say we do something like n1 times stride plus n2, right, to offset even further the index. So n1 is gonna be the row and n2 is gonna be the column. Does it make sense to put row? Yeah, it makes sense to put row and column like that. Okay, I think that should, but you know, this one is just a single byte. So we kind of want to modify this thing to be like a double and probably divide it by 255. Let's say that we have like double image already. Or this, yeah, image. Image to block. Maybe this is gonna be just lowercase x, or I guess block. Makes more sense to call it block. Okay. And I think we also want the reverse of this function, so block to image, block to image. Here the image should be a const as well, and here probably the block needs to be a const. Okay, so I would say we just have to do the reverse. So let's do it like this. So we just do the reverse, all should be good. So image to block and block to image should look the same, but they just set the indices. Okay, so maybe the first thing that we want to do on the bytes is to convert them to double, just to have something like that. So double pointer image, let's do a malloc. So size of double times width times height times num channels. So this is going to give us the image exit failure. Okay, and we might want to convert the bytes to float. So size to I, 0. And we can easily do that by just dividing by 255. So double bytes I divided by 255.0. Okay, so yeah, let's do lowercase x, and lowercase x we are gonna do image to block. And here let's use image ij as the indices, and then we want the stride, which is width times num channels, and then we are gonna pass x in here. Let's define both. Then we should be able to do dct block on x capital X, then inverse dct block on basically the same arguments, and then block to image. All right, so that's gonna be the way to we convert the image to a block, then we apply dct on that block, we do something here, we are gonna do something like add some information, then we do inverse, and then we switch back from a block back to the image, right? And we should be able to save the image, and it should look the same because we don't do anything. So let me just copy paste the save image from somewhere. Come on, where did I save an image? STBI load, STBI write PNG, yeah. So let's do write PNG, and it's gonna be Elena out.png. Okay, and let's try to run this thing. Did I forget the plus plus somewhere? Because otherwise why would it be so slow? Do some printfs, just make sure that everything is fine. So printf block %d %d. I guess it's ZU for this kind of numbers. Okay, I guess I forgot. What? Hmm. Wait, what? Huh? I mean, we have the Lena image, so that should be good. Oh, yeah, whatever. But why is the block so... It shouldn't be that big. Oh, I did I++ here. Now it makes sense. Now it makes sense. Okay, nice. So it actually went over all the blocks, and obviously it's 63 by 63 blocks, because if we do 512 divided by 8, it's 64 blocks, right? So it's just 64 blocks. Pretty small. That's why I was like, what the fuck? Where do I have the infinite loop? So let's check Lena out. It looks the same as expected. So DCT, I think it seems to work. I don't think it has any problems. So let's try to hide some information here. So as I said, for the information, we want to hide bits. So that kind of sucks. If you think about it, we have 64 by 64 blocks, so you can actually hide only this amount of bits, which is kind of crazy. So 512 bytes, which is 64k, which should be enough for everyone, right? So yeah, I mean, it's pretty small. But wait, I divided by 8. I'm stupid. It should be by 1024. Okay, yeah, it's not enough for everyone, sadly. So it's half a kilobyte. But it should still be enough for hello world. So let's do size t bit index. Let's make it simple. Size t byte index is gonna be 0. So we are gonna increment here the bit index, right? And if bit index, let's say it's greater or equal than 8, which is the number of bits in a byte, we want to reset the bit index. So bit index is 0 and byte index plus plus, right? We increment the byte index. And let's say we are gonna have a const message somewhere, like const char pointer message is hello world. And I think we also need the length. So size t message length strlen. I mean, we could say, I think hello world has a length of 12. I mean, that's pretty classic, but let's use strlen. Okay, so that's how we are going to increment the bit index. But now the question is, how do we get the bit out of the byte? So let's do yeah, sure, char byte is just message at byte index, so that's how we are gonna get the byte. And then let's do char bit is gonna be, it's basically gonna be byte, and we have to shift it. So I guess I'm gonna shift it to the right by 8 minus bit index. It doesn't matter that much, this thing, but it has to be consistent. Every time we do shifting, we have to keep in mind that we are writing most significant bit first from the bit. Okay, and then we end it with 0b, 1 2 3 4 5 6 7 8. We end it with 1 bit, right? And this is gonna make sure that let's make sure actually that the order of operation is right. I don't know what the order of operation is, honestly, for these operators, but whatever. So that's how we are gonna get the bit out of our message, right? And this will basically make sure that we iterate the bits. Okay, so let's see how do we write this thing. So also something that's I'm using Neovim. Also something that I noticed while testing was that obviously you might say, okay, but we have an 8 by 8 block, why not write in every float, or I guess double from that block? Well, the problem would be that some like frequencies, we can call them, have like a greater impact on the image. So if we use 0 0, for instance, the first index from the block, the result is gonna suck. But if we use indices from the middle of the block, it's better. So yeah, at the end, obviously you might be right, we can use multiple floats from this block to write data to, but let's just stick to one. And the one that I found worked was the ones with 3 and 4 in the name, in the indices. Okay, so let's do x at 4 3, and here what do I want to do is to convert, or I guess let's do double coefficient is equal to this thing, and then capital X at 4 3 is equal to coefficient, right? And we want to modify the coefficient. So the easiest way to do that, I guess we want to modify the last bit. So I guess I had a pretty cool formula in here, so let me just see, just because it was pretty cool and I don't remember how I managed to get it like that, but we can actually take a look at it because it's kind of cool. So if you have a float number, let's say x or whatever, let's call it a maybe, if you round it, then you subtract, or I guess let's pretend a is an integer for this case, so we don't have to round anything, we don't have to convert anything to int. Let's just say we have a. If you subtract a modulo 2 from it and you add a bit to this thing, if you, so let's say this is equal to C is equal to this thing, like the coded message. If you do C modulo 2, you actually get the bit value out of this thing, which is kind of pretty nice. And funny like parentheses on this thing, I was like, well, we have that math prover tool, right? What if we try to prove this thing in that math prover? That would be kind of cool. I mean, obviously we can try to do that. So yeah, why not? So let's go into proof. We don't have cargo, so let's I mean, it has to download all of this shit, so hopefully it's gonna be done quick. I guess never mind. We'll see when it's done, but yeah, I thought about it and it actually worked to prove this thing in proof, which was kind of funny. So yeah, like a would be an integer, then I defined this modulo 2 function, and if you open all the parentheses, and you get, a modulo 2 and then a modulo 2 twice, which is just a modulo 2, these two terms reduce with each other. So I mean, we can just do it in the comment. So it, you would get this thing minus this thing plus bit modulo 2 is just bit, and then obviously you still need to put everything modulo 2, but that's and this thing, if you modulo something twice, it's still that. And now you can see that these two terms are equal and you have a minus between them, so this would disappear from here, and then you have bit modulo 2, which is just bit. So that's kind of cool that you can just modulo the coefficient by 2 and you get a bit out of this. So that's kind of nice. So this should encode the message into the coefficient. So if we run this thing, we should actually see the image is the same, right? It looks kind of the same, but now we could try to get the message back. So how do we do that? Well, we need let's copy paste the entire for loop. We're gonna need some of it. So let's reset the bit index. Then let's say we're gonna need a byte. So char byte is equal to 0. We're gonna need a byte. And let's go over the thing. So we have I and j. So image is gonna be okay. So it's fine. We still have the image like this. Wait, am I stupid? Here I wrote the bytes. Okay, I have to convert the image to bytes again. But you can trust me that the image looks fine. So here it's bytes is image multiplied by 255. Maybe just making sure f max, f min 255.0 and 0.0. Just making sure that the image, let me just delete this part. Oh shit, we have some crap in the bytes. That's interesting. It's kind of weird. Oh, I mean, I have to do one. I mean, if I multiply the image first and then did that, maybe. I mean, it's still noticeable. In my other implementation, it wasn't. Weird. Huh. Curious why. Let me just double check. So inside of stag, now we were just doing the same thing, taking the coefficient, then doing this cool formula, then converting it back. Here I was also hiding the size of the payload because that's kind of nice to have, but I mean, I don't know, let's just use this one. Like here I was multiplying with 255 first, but I don't think it makes a difference. So normalized is just image for us. But again, I don't think that should make a big difference. Yeah. I'm not sure what's wrong then. I was also doing payload length, but I don't think that's important. Although it, kind of is, because if you go over the, like, I don't know how it works. it should get like a segmentation fault if you go above the payload length. But since it's on the stack, it should get just a stack overflow, so that usually doesn't crash the program, right? Anyway. Okay, I mean, I guess you can still see some artifacts. Maybe I didn't notice them in my original implementation, but whatever. Let's just go with it. Let's say, oh, okay, whatever. So let's take this thing and let's do char byte is equal to 0. So we kind of already know the message length. Let's just keep it like that. So here we want to convert the modified image to a block. We already have the modified image loaded already, so we don't have to do anything. Then we apply DCT. Then we need a coefficient, so let's do coefficient. Then we are gonna get the char bit, and as I said, this is just coefficient modulo 2. So that's all we need to do. Obviously we need to round it though. Round and convert it to int. Something like that. I don't know why I put those, but yeah. So that's gonna give us a number between 0 and 1, but I would still do this AND because that's kind of nice. Yeah, thank you. Thank you guys, thank you. Okay, so that's how we get the bit. We don't even need to do the inverse DCT anymore because we don't really care about it, but we just want to put the bit into the byte. So how can we actually do that? I mean, it's kind of the reverse of this thing from what I was saying. So let's think a bit about it. So we already have a byte variable. The reason why is because we need to write into it until the bit index is greater than 8. Hopefully it makes sense. So here we might need to do something like byte or, and we need to shift the bit to the left by 8 minus bit index minus 1. Probably that's it, if I'm being honest. And obviously here, once we go over, we have to set byte to 0. Maybe we also printf the byte. So let's just printf %c byte, and then we can printf a new line, just to make sure that we actually decode this properly. That's not what I expected to see. Byte or this thing. Let me check again in here as well. So that's how we do the encoding, and then the decoding is just, yeah, as I did here. I'm not sure, honestly. Maybe there's something wrong with something else. Let's printf the bit index. So zu bit index. Image to block. Okay, that's kind of strange. So yeah, we were converting the image to a block, then applying DCT 8x8. Maybe there's something wrong with image to block. Although here I think the implementation is a bit different. Not really, it's kind of the same thing. Block Y times, I mean, it's the same thing. But let's just, you know, copy paste this. But I mean, I notice a bit of a difference, but I think it's just the way I factor the terms here. So here it's n plus j, and in the other one it was, no, here it's j times stride and n times stride, but in my other implementation is j plus n times stride. So it's the same thing, I would say. Maybe, oh shit. Yeah, I think I forgot about the block size. That's why the image looked like this in the corner. So you can see that in the artifact part, it's like only in this part of the image. So the reason why we have these artifacts is that we write in the same place multiple times. So here when I convert, j should be multiplied by block size, and I as well, I'm pretty sure. So j and I should be multiplied by block size, because I and j are block indices, and here we are actually indexing in the image. So we have to convert from block index to image index. So we multiply by that. Okay. Let's take a look again. So get the hello world. That's cool. And the image, I mean, yeah, I can still see some garbage on the image, but on the left side, but it's like we actually got the message. That's pretty nice. Yeah, that's an absolute coding moment. right? So we were also able to decode, right? So like that's pretty much the main idea here. Probably I'll upload this as a gist because already did the implementation in the stake project. Doesn't really make sense to add that here. But yeah, as I said, here I did kind of the same stuff. Maybe it's a bit different because, you know, different day, I was working differently. But I was trying to test whether I would be able to add compression to this algorithm. As I said, here we only hide data in the 4.3 index, but we might be able to hide it in more indices as well, other than just 4.3. So yeah, I might want to have a look into the compression part. Like here, how can we hide more stuff? Right. But yeah, so if we run make, let's try to run hide DCT. So here if we echo hello into the image, hello world, it's gonna hide the image, and if we show DCT, it gives us back the message. So that's how it works with the CLI tool. So it's already integrated there. I just wanted to show you guys, you know, how I came up with the algorithm itself. So yeah, here maybe we can try to add more stuff, like somehow rotate between the coefficients. You know, I guess that's an interesting idea, rotating through the coefficients. I mean, what I could try to do is for size t k is equal to 0, k is less than compression, k plus plus, we could try to put this entire thing into a for loop, right? And as I said, try to somehow rotate between multiple coefficients. So maybe instead of coef x and coef y, we are gonna have y's and x's. And what if this thing is 4, let's do 4 4 3 3, and this one is gonna be 4 3 4 3, so we can have a compression of 4. But obviously this would be better to be a const size t4 is equal to this. What do I have to do? Wait, how? No. Size t. How do I declare like a global array? I read that down. Oh, it's like this. Yeah. And here it's y's, so it's 4 3 4 3. So maybe we can try to have something like this. So here it's coefs x of k, coefs y of k, right? And here as well, coefs x, y is at k. So maybe this could do some compression with byte index and bit index. The only thing we need to worry about is the byte index and the bit index. We need to take care of them here. Right, and increment them. Then DCT just works just like DCT. So this would add some, maybe, I don't know yet. I still have to think a bit more about that. So here, how can we handle the decompression? Probably with the same for loop. So here we get the coefficient at x is k and y is k. Right, so I think this should still work because I have a compression of 1 right now. But if we go to main.c, I think the compression is hard-coded for now. Yeah, let me just unhard code the compression. So let's add this argument, and let's do something like this. So we do compression level, size t compression level, default 1, and we should also have it here. Right, in the other function, and let's also parse it. Just like here, and then we are gonna replace that one with compression level. So here is gonna be ars.compression level, and the other one was here. We're gonna use the compression level. So now we can just still run it as usual, but if we add a C2, it doesn't work. So yeah, that's why I'm saying that some indices work and some other indices don't really work. But it's weird because we hid it in 4.4 and 4.3. Let's try, I don't know, 3.3. I'm curious also how the Elena out image looks like. Yeah, maybe it's something wrong here, but again, I'm not sure about the compression, how I could make it work, or even if it works actually on like if you modify multiple values in a DCT block, does it still work the same, or is it way too different? Not really sure. Because from what I tested, like 3.3 and 4.4, they are fine, but just make this thing again. Version 1. Let's see for 3.3, and I think even 5.5 is decent. No, for 5.5 it already doesn't work. So that's why I'm like, some values work, some others don't. I'm also curious if it works for all messages, but that's another thing. Yeah, so unsure about how we can put more data into DCT. It's like the smallest one so far. It's like you can barely hide hello world in it, basically. I mean, you can hide 500 bytes, but it's kind of small. But I mean, the upside compared to FFT is that you don't need the original image. That's kind of like a bonus. But yeah. Naturally, and maybe if you modify too many things in here, it doesn't work. So, or maybe my order is wrong. Though I don't think so. It's like bit index. I don't know. I don't think it's the order. Because we have the same stuff here. Yeah, I'm gonna say that, the order seems fine. I don't know. I don't think it's a problem, but I'll have to check. Like, compression would be cool to have. Imagine that it would basically double the amount of bytes you can hide. But yeah. So yeah, I guess that would be all for today. We managed to implement DCT. As I said, I think I'm gonna upload this as a gist, just so you can just copy paste it if you want to play with it. But the actual implementation is done in steg.c. So here I did I mean, it's the same stuff, but it's just refactored in a way, like in functions basically. So yeah. But yeah, that would be it for today. So we were able to let's run make again. We were able to hide a message into an image. The image looks the same. This time we used DCT as the algorithm. Let's just try to do from image some extra stuff. Let's see if it still works with a larger image, with a larger payload. Because I guess if it's too long, it doesn't show it as a string anymore. Is it really that long? Yeah, I mean, it got it right. Like 48 is an A. Actually, I don't know. I'm pretty sure this here is a hello, because I see C6, C6. Let's write it into a file. So output. Right, so we actually get the result. Sure, would be interesting to try and make a big one. So since we also hide the length, let's just make sure how big the length. So the length, it has 8 bytes, right? And how many blocks does it use? So it's 8 times 8. Because it's 8 bits per byte, so we get 64 blocks. So if we have 512 divided by 8, did I make like we have 64 blocks times 60, so it's 64 times 64 basically, this many blocks. So we only use 64 of them. So if I do A times 4000, we should be able to hide this thing into into our thingy. So let me just do Python 3-c, and then we are gonna do print a times 4000. So we should be able to hide. Maybe no. Maybe 100 of them. 100 of them, yeah. Okay, let's try to figure out what the number is. So 2000, too much. Oh, because it's 4000, so it's 4000 bits. Okay, so if you think about it, it's 4096 bits. So if we divide this by 8, 512 minus 64, 448. We can hide only 448. Okay. So if we do here 448, it should work. But if we try to do 449, it shouldn't. And I mean, I shouldn't do segmentation fault. I should actually. Okay, that's 460. Maybe I was wrong. But I'm pretty sure that 512 shouldn't work. 504, maybe I did. Okay, so I computed that wrong. I guess we have to subtract only 8. Yeah, whatever. No. The fuck? Ah, it's because I'm a print. Okay, print adds an extra new line at the end. Right, so that's why it wasn't working. Interesting. So it uses only 1 byte? The fuck? I mean, yeah, that's kind of interesting. I'm not sure why it uses only 1 byte for can I do word count characters? Yeah. Yeah, I mean that's interesting. I'm not sure exactly. I also need to check that. Maybe it's because I was expecting to see maximum 512, but since we also put the length in the payload, then it should be less than 512. And I mean it is, but I was expecting a lot less. Yeah, I mean you can see some artifacts on the image, but I think it's fine. So yeah, I guess that would be it for today. And let's see in the next one. So until then, see you.